Hello. We present GaussianFlow SLAM, a monocular Gaussian splatting SLAM guided by GaussianFlow. Recently, 3D Gaussian splatting has emerged as a powerful map representation enabling photorealistic 3D reconstruction. To extend 3DGS to the SLAM, various sensor configurations have been explored. For instance, the method based on RGBD camera, which can provide depth measurements, have been extensively researched. Meanwhile, 3DGS SLAM based on monocular camera has also been explored. Several algorithms have shown that 3DGS can be successfully extended to monocular SLAM in environments confined to limited spatial scales. However, as the spatial scale increases, monocular 3DGS SLAM begins to struggle. Let's look at some recent methods in such an environment. MonoGS performs multi-view optimization on manifold for accurate pose estimation and obtains feedback from 3DGS for pose estimation to leverage the advantages of the new map representation. However, it lacks cross-view correspondence constraints, making it prone to local minima that cause overfitting to specific views. PhotoSLAM initializes Gaussians using the initial 3D points provided by a feature-based SLAM system. This gives a reasonably good initialization, but when the features are sparse or noisy, the map becomes unstable. Moreover, since it uses a separate tracking algorithm, it does not obtain any feedback from 3DGS for pose estimation. To overcome these limitations, algorithms utilizing monocular depth estimation network have been proposed recently. MM3DGS SLAM provides initial Gaussian positions using a monocular depth prior, avoiding issues from point sparsity. It estimates poses by obtaining feedback from 3DGS through its rasterized depth and color. However, if the scale ambiguity of the monocular depth prior is not properly handled, it can cause geometric distortion and make the system unstable. HiSLAM 2 also provides initial Gaussian points using a monocular depth prior and achieves robust performance through an optimization-based scale alignment module. However, when the depth prior is unreliable, it struggles to form valid geometry. Moreover, it does not utilize 3DGS to obtain feedback for pose estimation. Our GaussianFlow SLAM uses dense optical flow as a geometric cue. By leveraging the cross-view correspondences provided by optical flow, our system can continuously correct geometry, even when it is initially inaccurate. Our method does not require scale alignment, and it utilizes Gaussian flow from 3DGS for pose estimation. This figure illustrates the overall process of our method. As shown in the video, the process begins with initial mapping, where the inaccurate geometry of the initial 3DGS is gradually corrected. When a new monocular image is received, the initial pose is estimated by minimizing the loss between optical flow and Gaussian flow. Then, Gaussian flow-guided DBA and mapping are performed alternately in an iterative manner to optimize geometry and poses. Here, these three core modules perform a recurrent update process. Each module has its own optimization kernel, which outputs pose estimation results or 3DGS updates. The Gaussian flow obtained from 3DGS is fed into a conned GRU, where it guides the optical flow, influencing the outcome of the optimization kernels. Through this process, the optical flow and Gaussian flow gradually converge to similar values. Meanwhile, during mapping, the error-based densification and pruning modules are performed. The proposed normalized error takes each Gaussian's coverage into account, allowing the system to appropriately select Gaussians for splitting or pruning. These modules help correct the geometry, leading to a more stable Gaussian flow. Now, we showcase our demo videos. Demo number 1 and number 2 present the performance and operation of the proposed method on the TUM RGBD and EUROC datasets. Demo number 3 compares the effectiveness of our error-based densification and pruning modules against original densification and pruning modules in 3DGS. As shown now in the MH05 sequence, our method continuously corrects geometry using Gaussian flow, successfully forming valid geometry even in a challenging scene. In this demo, we showcase a comparison with ODP. You can see that when ODP is used, overly small Gaussians receive negligible gradient updates, leaving noisy artifacts in the scene. In contrast, our method performs proper densification while pruning such Gaussians, resulting in higher quality scenes. Thank you for watching the video. Please refer to our paper for more details.